In this video, we focus on section 3.6 on the mass spring damper system again, which is what this section 3.6 is all about, but we focus particularly on what we're going to call the new parameters, which are called omega and delta. Okay, the omega and delta parameters are slightly different than the ones used in the book, and so let's take a look at what the book does, and then we'll compare it to what our preference is going to be. So in the book, they're considering the differential equation my double dot plus by dot plus ky is equal to 0. And so, for example, in the differential equation y double dot plus 4y dot plus 13y equal to 0. M is equal to 1 for the mass of the mass on a spring, how much mass is there, for example. B is equal to 4, and this is related to the amount of damping that's present in the spring system, and K is equal to 13, which is related to the stiffness of the spring. Okay, so you imagine that you have a mass on a spring, right? The spring stiffness is K, and you're imagining that there's this mass is maybe like in a shock absorber system, and there's immersed in some sort of fluid or whatever that applies some sort of damping force to the mass on a spring. Okay, so that's what the book does, and then they will, perhaps divide through by M. Divide through by M because you have a 0 on the other side, so you're allowed to do that. And then they'll turn this second order differential equation into a system using the following method. So this is a matrix that often comes up in the textbook, and I think they'll call this matrix 0, 1, negative P, negative Q, where P is equal to K over M, and Q is equal to B over M. So the book uses, you'll often see the variables P and Q, or they'll use the M, the B, and the K, all three of those variables. Or they'll use the two new parameters, P and Q. My preference is to, our preference in this class is to look at this differential equation y double dot plus b over m y dot plus k over m y. Start here, and then we're going to introduce new parameters. Let omega be the square root of k over m, and we're going to let b over m equal to delta, which implies that delta is b over 2m, and omega is the square root of k over m. Okay, delta and omega are going to be our parameters. We're going to use delta and omega instead of the parameters p and q. Okay, so for this example, if the mass is 1, B damping is 4, and K is 13, then this will tell us that omega is going to be the square root of 13, and delta is going to be equal to 2. And what's going to be really interesting to see is that it's not omega and delta that we'll find show up in the formulas that we're going to need. It's going to be omega squared, which is 13, and delta squared, which is equal to 4. Okay, so these are the values that are going to be of importance. Okay, so I would like to look at an example, kind of examples that illustrate the meaning of the variables delta and omega. Okay, I think a good example of illustrating omega can be obtained if you look at the differential equations demos that we have on our website for Mathematica. And you get the options here to put in your various values for M, B, and K. You get to put in your initial conditions for this second order differential equation for the mass spring system. And you run this code by highlighting it and hitting Shift Enter. And this is the code that will appear to you. Okay. It tells you what you've input. You've input M, B, and K, and then it tells you what omega squared and delta squared is equal to. Okay, so for the example where there's no damping, B is 0, delta will come out to be 0. And when K is equal to 4 and M is 1, omega is the square root of K over M, which is the square root of 2. Square root of 4, I'm sorry, which is 2. Therefore, omega squared is equal to 4. Okay. If you follow through with this procedure, look what happens. You can find your characteristic equation. Okay. Your eigenvalues will come out to be plus or minus 2i. Okay. Which implies, let me bring it over here. So notice that the eigenvalues came out to be plus or minus 2i, which is another way of saying 0 plus or minus 2i, which means that for our mass on a spring, okay, the 0, the real part of the eigenvalue, became e to the 0 times t, and then we knew that the 2 was going to show up in front of the t terms inside of the trig function. So these means the 2 is showing up in the angular frequency term of the trig functions. Okay. And now if you proceed with finding v of t, right? You could take the derivative to get the derivative of cosine is negative sine, so negative 2c1 sine of 2t, and c2, the derivative would give you plus 2c2 cosine of 2t. And then notice that you had initial conditions for your differential equation of 5, 0. Okay, so you had initial conditions of 5 and the initial velocity of 0, which you can use to solve for C1 and C2. So if you solve for C1 and C2, you'll get y of t. Okay, you'll see that y of t comes out to be 5 cosine of 2t. And as promised, v will be the derivative of y, which will be negative 10 sine of 2t. Okay, so what we're trying to figure out here is this example, there was no damping, so delta came out to be 0, but we did have an omega term. Omega was 2, and we can see that omega equals 2 is showing up in the frequency part of the solution for y. So if you look at the time plots for this differential equation, right, here is a solution for y. Y is the dark solid line. Okay, and the trick here is to remember the formulas for t is equal to the period of the oscillation. Okay, and it's 2 pi divided by the angular frequency omega. So it says that the period is going to be 2 pi divided by 2 because omega was 2, so the period comes out to be pi seconds. Okay, so if you're looking on the graph here for y, if you look at how long it takes to go from a peak here to a peak here, that time is a little bit more than, here along the t-axis, a little bit more than 3, which is exactly what pi is. So pi is how long it takes for this graph to go from its peak to peak time. So that is the period t. And that's related to 2 pi divided by omega. Okay, your textbook defines something called f, the natural frequency, and that's 1 over the period. And the period was 2 pi divided by omega, so the natural frequency is omega over 2 pi. So sometimes the book will use the terminology natural frequency. And omega shows up in both those formulas for the period, and it also shows up in the formula for the natural frequency. Okay, so that's the meaning of the variable omega. Okay, if you add some damping into the problem now, let's let damping be equal to 1. B is equal to 1. Okay, let me see. Hold on a second. I gotta find the number that was going to work out nicely for us. Where did that one go? Alright, 1 second. So B was oh, that's right. Let's look back at the example that we had. K was equal to 13 and B was equal to 4. Okay, and let's set the initial condition y of 0 to be 0 and the initial velocity to be 0. Okay, now we know what was going to happen here. We had eigenvalue -2 plus or minus 3i. Okay, so that led us eventually to the -2 term, and the eigenvalue appeared in the exponential, e to the -2t. The 3 appears in the frequency term of the sine and the cosine, and the C1 and C2 are going to be those coefficients there multiplied by 5/3. So that would give you your C1 and C2. Okay, let's look at that case real quick if we could. So notice that we recover what we expected, that if the differential equation was y double dot plus 4 y dot plus 13 y equal to 0, then we had b was equal to 4, k was equal to 13, and m was equal to 1. That leads us to omega was the square root of 13, so omega squared was equal to 13, and b over 2m is equal to delta, so that led us to b was 4, 2 times 1, so that led us to delta was equal to 2, so delta squared is equal to 4. And that's what the code here is reminding us of. Okay, and you then know that the solutions are going to be oscillations. And let's zoom in on this plot a little bit and bring the plot time down a little bit. Okay, so what we're seeing here is oscillations for y. Okay, and the oscillations are getting smaller and smaller because of the damping delta term. We're getting e to the -2t in front of there. But if you could look at, if you could see the peak-to-peak times, the period would be 2 pi divided by omega, which is the square root of 13, and the natural frequency f would be 1 over the period, which would be the square root of 13 over 2 pi. Okay. So if you can look at the plot over here to the left, and if you could plot that for a little bit more time, it's a little hard to see. If I could zoom in a little bit more, the peak to peak time there, probably somewhere around there to there, from peak to peak would be about 2 pi over the square root of 13. Okay, convert that to a decimal and you can compare it to the plots. Right, so that's the meaning of our variables delta and omega. In the next video, we'll show how to completely solve the mass spring system just knowing the values of delta squared and omega squared.